Okay, should be recording. So let me hand the floor over to group 4 and let them give us their presentation.
All right. Hello, good morning, everyone. This is the presentation of Team 4, the Tri-beam Solar Automated Reflector, known as SAR. The SAR is a heliostat module that allows the collection of solar thermal energy to generate electricity. To understand the importance of the heliostat design, it is first important to understand the benefits of CSP, so concentrated solar power. Our design is a power tower configuration in which all the heliostats reflect the solar energy to a central receiver, which will later produce electricity. The field layout is covered by heliostat, automated mirror surfaces, which will allow the concentration of sunlight in this tower. A benefit of the CSP is the low cost of storage, because CSP stores thermal energy rather than electricity, like photovoltaic energy generation devices. CSP plants can produce electricity up to 10 hours after being exposed to the sun, so without any sunlight, for instance, at night. Additionally, this project is also a small scale heliostat. Some of the benefits of going small scale can be describing some of the research that we did, which came out to be the decrease of losses due to tracking, the ease of manufacturing in already established assembly plants, the use of already existing off-the-shelf parts, and a simpler transport of the modules to the field. So without any further ado, welcome, and this is the SAR.
This is a visual rendering of our proposed solution, the SAR. From the provided images, the front and rear side of the heliostat module can be seen. Our main design goal for this project was to create a heliostat module that used the least number of motors per individual reflective surface. Using as few motors as possible while still allowing independent rotation of each reflective surface strikes the perfect balance between simplicity and functionality. Having less motors reduces the cost as well as potential risk of failure of the system and allows the system to be easily repaired and maintained throughout the future. With the same angles as before, the SAR can be identified by its 3 subsystems. From top to bottom, these subsystems include the reflection, platform, control, and frame subsystems. Here we have the design field layout for the heliostat module. In order to meet the power production needs, 2.61 acres of land are required with an aperture height of 28 meters. The SAR array consists of 29 rows, where each row is spaced by 4 meters in order to accommodate traditional sized cleaning vehicles. The array is arranged where each heliostat module has an angle biased towards the tower in the center, as this allows for a greater solar concentration. Starting from the bottom of the SAR is the frame subsystem. The needs identified for this subsystem include the heliostat count, shading, cost, area ratio, percentage of off-the-shelf parts, module spacing for cleaning, and the topography of the location. The frame addresses these needs by supporting 3 heliostats per module, all of which are placed in a row to prevent cross shading. The cost is addressed through the material selection, where the chosen steel square tubing is less expensive than the alternative steel stock. Furthermore, to accommodate the provided topography, the frame and support wheels provide a firm structure to the overall assembly.
So for our first subsystem, the frame, it is manufactured using 3/4 inch steel square tubing, which is welded together. The central motor that is mounted to the frame, which controls the control platform, allows it to rotate laterally, is an EML4501 motor with a 100-to-1 gear reduction ratio to increase the torque due to the weight of the control platform that's required to rotate. In the center there of the frame is our computer control housing. And within that, we have one computer, which is a Raspberry Pi Zero W with Wi-Fi capabilities, and 4 motor drivers, which are the Big Easy motor drivers by SparkFun. Each of these motor drivers are designed to drive a singular motor. So that's why we have 4, 3, for the upper motors, one for the central motor. To connect the central motor to the control platform, we have a custom-made shaft coupler that's made from aluminum. This is welded to the control platform, which is an aluminum structure, and then it's connected to the shaft using 2 set screws. So from these 2 views, you can see the electronic housing in the frame. So we created a sheet metal shielding that connects using screws and rivet nuts into the frame tubing. So the shielding is entirely removable. You just have to unscrew the rivet nuts. You don't have to remove any more parts to allow for maintenance of the computer systems. On the right view, you can see the shielding removed, and all of the computer parts are connected using standoffs to the upper steel plate that's tapped for the holes. We have 3 motor drivers on the left side, and then the computer and 1 motor driver on the right side. The shielding features vents on the bottom to allow for circulation of air to dissipate the heat put off by the motor drivers. So to determine the heat transfer capabilities of our motor drivers and our enclosure, we performed a heat transfer calculation on the heat sinks that we'll be using on each of the motor drivers. The compute units on the motor drivers each have 1 heat sink. They're very tiny heat sinks, and they're attached using thermal glue. And the heat sinks feature rectangular fins. So we did a calculation for a fin of a rectangular profile with an assumed adiabatic fin tip. So there will be no heat transfer through the tip of the fin. So to start this, we calculated the Reynolds number. And for the velocity of the air, we used 0.1 meters per second, which is a standard for a limited airflow enclosure with some circulation, but very limited, which would be provided by the vents. Once we found the Reynolds number, which was 1.05, the range that we used was between 0.4 and 4. So with that range, we could find the Nusselt number using this equation. And the Prandtl number was also greater than 0.7 for the air temp. So using the Nusselt number, we were then able to calculate the heat transfer coefficient. And then using the heat transfer coefficient, we were able to plug that into the heat transfer equation and determine that for the heat sink, each fin would dissipate 0.624 watts. Because the heat sink has 5 fins, the total heat dissipation would be 3.12 watts. So we compared this to data we found on a PDF for the specs of our motor driver. And based on the operational conditions that we would be subjecting the motor drivers to, the compute units would be utilizing 3 watts of power. So based on this calculation, because our heat transfer is greater than 3 watts, we will not see any heat transfer issues or overheating of the chips.
So this slide gives a visual representation of how we're attaching the control system, which is the aluminum tubing on the top, to the frame, which is the bottom component. It's all steel. And essentially, like you mentioned before, we have a central computer housing, which you can see on the left image, and that contains all of the motor drivers and the Raspberry Pi Zero W. We're using locking grommets for wiring throughout the module. And so on the top, we have locking grommets in each of the vertical beams, and on the bottom, the frame, we have locking grommets going into the computer housing. That allows us, like you said earlier, to fully remove the computer housing sheet metal without having to, take any of the wiring out, such like that. And so for the wires, we're using 26 gauge wires. And for the top motors, since the control platform is rotating, we're wrapping the wires for all 3 motors in a wire loom and putting that around the shaft coupler. So the image on the right gives a representation of what it would be in the most extreme state. So this would be after it's rotated 180 degrees to track the sun. And then at this point, we would need to use computer software to tell the module to rotate the other way so it doesn't keep wrapping the wire. And we also determined that using 26 gauge wire, the top motors need 1.7 amps, and the motor drivers we're using with a heatsink provides 2 amps. The motor drivers also provide 30 volts, which we would end up losing about half a volt with the distance wire that we need to get up to the top motor, but the top motor is only 24 volts, so we would be fine.
In this slide, you can appreciate the free body diagram that the team generated to account for all the forces acting on the system. These allow us to provide stability and static equilibrium in the system. As we can see, the 1.88 kilograms are described as based on the weight of all the components that we have. The 1.88 kilograms represent the motors and the reflection platform, while the 0.44 kilograms represent the weight of the beams, the vertical beams of the control subsystem. As you can see, reactions 1 and reactions 2 are actually accounted for the wheels, for the support wheels that we have on the control subsystem, while reactions 3 and 4 in the red indexes are the reactions of the ground to the frame. And although, as you can see in the free body diagram, the calculation of the forces allowed to obtain a static equilibrium of the system, that's not our main concern in this project. Our main concern in this part is the torque calculations that we need to generate, or that we need to account for the central motor to move. As you can see in the torque calculations, we are accounting for the 1.88 plus the 0.44 kilogram of the structure plus the beam. And we're multiplying that by the acceleration of gravity, 9.81. And that times the distances that all of these forces are acting on the system. This will give us a final torque of 16.7 Newton meters, while the motor that we are using provides a maximum torque of 25 Newton meters. This will allow us the conclusion that our system is actually capable of moving, and it's not forcing the motor at its max capacity.
The customer needs listed for the control platform include an operational lifetime of at least 20 years, which is met by using an aluminum rust-resistant platform. Parts must be equal in price or less expensive than the closest available or over-the-shelf part. 55% of our control platform cost is from over-the-shelf parts. The stepper motors are computer-controlled and capable of 200 steps per rotation. The cost was minimized by using thin aluminum square tubing, which is less expensive than aluminum stock. The stepper motors each allow for a 180-degree rotation to redirect sunlight to a central tower up to 100 meters tall. The control platform features a tri-beam-like structure constructed from aluminum square tubing. The system is secured to the frame via a main central motor, which allows the SAR to fully rotate about the vertical axes. At each end of the control subsystem, there is a wheel which prevents an internal bending moment within the control structure. At the upper end of the control subsystem are 3 independently functioning motors. These motors provide a second axis of rotation to the reflection surfaces. The wheels serve a vital purpose in the structural security and overall functionality of the design by reducing the stress on the drive motor. Without the wheels, all of the weight and balancing stress would act on the central motor shafts.
So here we have a close-up view of the top motors that turn the reflection platform in the vertical direction. We're using a NEMA 17 stepper motor here. It's got a 5.18 to 1 gear reduction. It's a planetary gearbox. This motor takes, as we said in a previous slide, 1.7 amps and about 24 volts of electricity to move. And that provides a 3.7 Newton meter torque. Our original design of the motor mount here did not feature a radial support ball bearing. However, during wind calculations, we determined that we would need one, and that's shown in a later slide.
The torque for each stepper motor can be calculated from a force of 15.5 newtons and a distance of 26.3 millimeters, resulting in a torque of 0.41 Newton meters. The torque provided by each motor is 3.7 Newton meter.
The reflection platform consists of the 3 mirrors and their corresponding support structures. So the needs identified for the subsystem included the reflection area, the tracking errors, cost, percent of off-the-shelf parts, washability, power, concentration ratio, dispersion, and the Las Vegas location. The cost was addressed through material selection analysis, which resulted in the selection of silica glass. The total reflection area was calculated by summing each of the 3 individual reflective surfaces, the area of each one, and that resulted in a total reflection area of 1 meter squared for each module.
So here we have the design process for finding our aperture area, the area of the target, which we're shooting our solar beams at from the mirror. One of the customer needs specified that we could assume a maximum tracking error of 0.5 degrees. And they wanted us to mitigate losses to be less than 40%. So we opted to try and keep that around 30%. And this is some of the calculations in order to find the aperture area that would allow us to maintain at least 70% of the reflected image.
So the total reflected power for a single module was calculated using the average solar irradiance, which is 1,000 watts per meter squared. And the angle of the reflective surface was assumed to be 45 degrees with the vertical, as that's the median value of the range of positions it can take. And the total reflective surface area and the reflectivity of the mirrors was also used, and that resulted in a total reflected power of 0.66 kilowatts for a single module located in Las Vegas. The useful thermal input power per unit time for all of the modules in the field was calculated using the reflected power by a single module, the average optical efficiency, and the number of modules. And then losses due to re-radiation were accounted for by assuming the sun was a black body with an emissivity of 1. And it had an emissivity of 1. And using the area of the receiver, the Stefan-Boltzmann constant, and the receiver temperature, the number of modules needed was 2,268. And the total power is 1 megawatt. The concentration ratio was determined using a ratio of total reflection area to the receiver area. And this ratio was multiplied by the optical efficiency to account for losses and the number of modules in the field. And that resulted in a concentration ratio of 1,095 suns.
So one of our concerns for this module was, having a wind speed that would cause the vertical beams that are holding the reflection platform hitting a natural frequency, which would cause, the system to go, crazy and maybe hit other reflection surfaces. And so in order to determine what wind speed would cause this, we used the natural frequency of a cantilever beam. We assumed that the vertical beams supporting the reflection platform were fixed at the horizontal beam. And so we assumed it to be a cantilever. And so to find the natural frequency, we use the equation above, where we use the point force for the reflection platform, all of that going on the central motor, and then the wind on the vertical beam as a distributed load. And so we found a ASCE standard that said at 1 hertz or anything under 1 hertz was where a structure would be considered, flexible or no longer rigid. And so we found the wind speed that would cause the frequency of the vertical member to go below that, which was well over 200 miles an hour. So it wasn't really a concern for us. We also wanted to determine the deflection needed, or the wind speed that would cause deflection in order to kind of bump mirrors. So the left mirror bumping into the center mirror. And to do that, we use the equation for deflection of a cantilever beam. We have the same wind load that we showed in the previous slide, where it's a distributed load over the entire surface area of the vertical beam and of the reflection platform from the side. And so to account for this, we have a spacing between mirrors of 14.1 millimeters, and the maximum wind force that would be needed to cause the left mirror to hit the center mirror would be 52 newtons. And that we used a wind speed calculator to figure out what that was. And it was 87.5 miles an hour over that surface area.
Another one of our concerns in relation to wind force is the maximum wind force that would be required to remove the reflective surface from the support beam that it's adhered to. So the adhesive that we used is JB Weld, and we chose JB Weld because of its very high tensile strength of 34.6 megapascals. So calculating the wind force, the maximum wind that would be required to overcome this tensile force of the JB Weld would be excessively high. It would be over 200 miles per hour. So we determined that the wind force in this case would not be the limiting factor for the maximum that could be withstood by our assembly. So another consideration was the wind force that would overcome the shaft rating for force in the radial direction of the upper motors that control the reflective platform. So the maximum radial force that the motor shafts are rated to is 80 newtons. And without the support bearing that we mentioned previously, the maximum wind speed that these shafts would be able to withstand was only 34 miles per hour. So including the new roller bearing design, we were able to increase the maximum wind speed by more than a factor of 2, up to 90 miles per hour.
So this shows some of the design iterations that we went through with our design. Originally, this was a problem area because the original thrust bearing that we decided to use, where the force F2 is pointing, was not able to withstand wind speeds past 15 miles per hour. So given that that was unacceptable, we decided to find a better bearing. And so we put a better bearing in there, and using a summary of forces, we found that the wind speed required to damage this bearing would be significantly higher at 69 miles per hour.
Another potential failure mode that we saw was, so we have a reflection surface, we have a mirror that's attached to a vertical welded steel or aluminum frame in an eye configuration. And so it's backed by adhesive. But one of the problems that we saw was that we had, a mirror overhanging the vertical part of that beam, and that could potentially snap since the glass is fragile. So that was a concern that we had, but we actually went out and purchased the mirror that we were going to be using. And, one of our members had a glass cutter, and so he was cutting it to the right sizes and everything. And we, did some other tests on it, but this was one of them. And so we wanted to do the same overhang and assume this to be a cantilever beam, since the overhang is pretty much fixed at that horizontal member. And so you can see in the right figure, we're pretty much doing the same configuration that the wind speed would be acting on. And so that gallon of water, it's 36.9 newtons. And we did the same overhang, which was about 7 inches. And to break that glass, the gallon of water was just about to break the glass, but so we assumed that to be pretty much the maximum load that it could take. And that would end up being 52 miles an hour. And since this was the lowest wind speed that we had, this ended up being our maximum overall wind speed in a fully horizontal configuration, which would never be the case, but we wanted to do it for, worst case scenario. And if you go to the next slide, we can see we ended up making a safety mode for our module, which would be the mirrors going completely horizontal so that it's minimizing the surface area that the wind is hitting. And we use a factor of safety of 1.2. So the module would enter this mode at 43 miles an hour, and the maximum that it could take, or that we would be comfortable with it in, would be 87.5 miles an hour, which is what we found earlier for the deflection for one of the vertical beams to hit one of the mirrors next to it.
So here we have a brief cost overview for the entire design. For the material cost, we got a total of $193. We wanted to really emphasize how detailed this cost analysis was. This is including wiring, and thermal paste, electrical tape, and stakes, and everything you would need, absolutely everything you would need to make this a real life heliostat. And the manufacturing cost came out to be $198. That's for welding the thing together and drilling the holes and everything. And it also includes assembly time. So if you were to pay somebody to completely assemble these heliostats, that would be included with this manufacturing cost. And finally, to power all of the 2,200 plus modules that we have in the field, it would cost about $40.66 per day, assuming a 10.5-hour day of operation, and that's taken at a price of 0.14 cents per kilowatt hour, which is slightly above the average. And we also wanted to highlight some of the key features of the TSAR that we think we really hit home with this design, and that's through the creative use of our motor design. We feel like we struck a perfect balance between motor cost, heliostat performance, and electrical efficiency. We also have a very economical reflection platform. So we wanted to highlight the fact that if this reflection platform were to ever get damaged, say in hail or in an extremely quick hurricane or such thing like that, it would be very, very cheap to replace this reflection platform. It also features a very sturdy frame. The frame for this module would completely outlast its electrical and motor components. So if you were to use this for, say, over 20-year lifetime, you could simply replace electrical components and you should have an entirely new field. And lastly, we wanted to highlight the fact that our motors have gearboxes, and the gearboxes represent about 70% of the cost of the entire motor system. So you could replace the motors and keep your gearboxes for over 20 years, much longer than 20 years. So there's that. And lastly, we wanted to thank you for letting us walk you through our design. And we would like to open up the floor to any questions or comments you may have. Thank you.
Okay, great. So we've got about 13 minutes left in the 45-minute session. So we'll open the floor to questions or comments from our panel.
Hey guys, this is Tom Singer from Northrop Grumman. I know we talked a little bit during your poster session, and I'd asked about the stability of the system where you have the I guess the wheels oriented in parallel to what winds up being a sail in the wind. Is there any thought about iterating that design and adjusting that moving forward? Because right now you've got a lot of force being wind force being impinging a good distance up, and nothing really providing stability to that except for the axis of that vertical motor right there. And that's a significant concern for me.
Absolutely. I can take the beginning of this question if someone wants some of my team members want to take later. If you can go to the slide of the safety configuration, we did consider changing the orientation of the wheels to account for the forces of the wind that are going to be acting on the system. However, one of the things that we did notice is that the safety mode doesn't necessarily need to only move the reflection platform. We can also move the control platform. So instead of allowing the wind to pass through these three openings that we have in here, made like like this by the control platform, we can rotate it to match the direction of the wind. In which case, the wheels will actually be parallel to the wind direction.
Yeah, I'm not so concerned about it in this orientation. I'm concerned about it when it's a 40-mile-an-hour wind and it's gusting to potentially higher than that, depending on how you figure out how this is going to work. But in a 40-mile-an-hour wind, I wouldn't want to put 40 miles an hour on a 1 meter surface that is basically free to rotate about those axles. That's a pretty significant concern. So there's that. While we're on this slide, you've got a factor of safety of 1.2. Is that acceptable to your customer? Because that is very sporty, as we say in the business.
So we chose that. You could choose. You could program your computer to put it into the safety mode whenever you chose. So if the customer would like, you could change that. But we chose this because in my mech design courses, this typically is the safety mode that we would assess at.
At a 1.2 factor of safety?
Yes, sir, usually.
Coming from the world of airplane designs, right? We keep things at 1.5. Unmanned rockets are at 1.25, and those are systems that are severely weight constrained, right? You're sitting on the ground, you're not really going anywhere, so you don't have weight constraints. I would expect to see a significantly higher factor of safety on something like that, where if this thing falls over, you're shattering a mirror, you're doing significant damage, and maybe the cost is such that that's acceptable, but I would confirm that that's acceptable with your customer. Particularly because as that safety factor goes up, the wind speed that you can tolerate is going to go down, and that limits the utility of a system like this, right? If you can't survive more than 20-mile-an-hour winds, if it's going to be that windy on a majority of the days, that's a significant problem for a system like this. Let's see. You've got it looks like a glass surface that is underlaid with a reflective mirror coating.
Yeah, that was a slide of the go up. Yeah. Slide 19.
Okay, so what protects the back of the coating from being abraded by dust particles being blown by the wind?
Well, if I can take this at the beginning, Brandon, you can take it later. One of the things we did was run one of the tests to see the reflectivity of the mirror, and we noticed that the glass is actually protecting the reflection part of the coat that really we are concerned about. The back side of the mirror can get dusty, and that can be related to the cleaning. That's going to be something we have to deal with, the cleaning, maintenance of the mirror. As we can see, some of the actual heliostat fields are cleaned on a bi-weekly basis, or some of them even like per month basis. So we are assuming that we are going to have these cleaning services as well.
I wouldn't be as concerned about cleaning the glass, although potentially things scratching the glass are going to impact the efficiency of your system. But I wouldn't expect any cleaning to happen on the back of these, especially if it's being serviced by some sort of system that's mounted on a passing truck. But I guess I would have a concern about dust blowing and abrading the reflective coating on the backside of these mirrors. If that's exposed, that's a concern. I don't know how much of a concern it should be, because I really don't have a lot of experience with mirrors mounted outside, but that's something I'd wonder about.
I actually went out and purchased this mirror to do the destructive testing on, and it has an acrylic paint on the back of it, so it would be protected from dust. However, physical objects, it wouldn't.
So this is just a commercial, a mirror that you'd find in Home Depot?
Yes, sir.
Any concerns about that being out in an outside environment for a 20-year period?
Actually, that was one of the things we did want to mention. We noticed that the reflectivity and the performance of the mirror outstands the cost outstands all days compared to the actual industrial mirror that we could be using. We are talking about the cost of the mirror to be less than $5, with a reflectivity of roughly 93%, where we can get this reflectivity up to 98%, but with a much higher cost, even going over $100 for a square meter.
Okay, because I'll just say that I know the mirrors in my bathroom, just from being in a humid environment, which Las Vegas isn't necessarily a humid environment, but the backing on those mirrors, right, it starts to get that little creeping sort of like black. I don't know if it's oxidation or what it is, but I wouldn't expect these necessarily to be a given to last for 20 years out in an environment like that.
I think humidity would be the concern with that, and I don't have an answer for that, but I do know that having these out, I did a lot of sun testing. I put them out in the sun for hours on end, and they did not get very hot. So I don't think the sun degradation would be a problem, but humidity is a very good point, actually.
Yep. And additionally, I did want to mention that after running more tests with humidity concerns, we could potentially generate a previous installation procedure where we paint the mirrors, the back of the mirrors, with some protective. We give some protective coat of paint, so that can actually be tested, and we can do some procedures for that concern.
All right, I'll step back. I'll let some other folks ask questions because Dr. Chow says I got 5 minutes left.
Thank you very much for your question.
Okay, other questions from our panel? We do have 5 minutes left. That wasn't meant to cut off the conversation. It was just to give everybody fair warning about time. So
yeah, I have.
Go ahead, Fred.
Lower motor, I know you looked at the torque applied to what I think was the upper motors. Did you consider the torque on the lower motor? Because that has the entire force of the 3 mirrors, and it just,
Yes.
yeah. Can you talk about that a little bit? Thanks.
Yeah, so this is the torque of the central motor. This motor is attached to the frame subsystem, the steel frame. This is our biggest motor, the one that has the biggest gear ratio, while the other ones are also the same motor with a smaller gearbox, but they attach to each individual reflection platform. That is actually one of the features that allow us to keep the losses under 30%, is that we can individually rotate every reflection surface instead of rotating the whole structure, the whole module at the same angle.
So is this torque the actual torque of the motor as in spinning the assembly, or is this the torque of the wind blowing on the mirrors trying to bend this backwards, sort of applying torque to the shaft out of the axis that it's intended to rotate?
So 16.7. Oh, no, go ahead, Brain.
This is the torque required. This 16.7 Newton meters is the torque required to move it without wind. The max torque of the motor there is what actually it's limited not by the motor but by the gearbox. These gearbox, it's 100-to-1 gear ratio on that planetary gearbox, and planetary gearboxes don't have the strongest of gears in them. So that's actually regulated by how much force the gearbox can take. So the wind force, we were considering that. However, we thought since the mirrors are particularly symmetrical about the motor, these vertical bars are not, the mirrors are. Right in the middle of this mirror is right on the axis of the motor. We would assume, we assumed that a lot of the wind force would be distributed across, and so there wouldn't be a humongous turning force on these.
Right. So I guess my real concern is in the other direction. It's a little hard to explain, but if you grab the center tine, if you will, if you look at this as a 3-pronged fork, you grab the center tine and pull that backwards, you're putting a lot of torque on the shaft of that motor at the bottom. And it's very low and the force is very high. So you're putting quite a bit of force with a leverage on that shaft, so out of the axis that it's intended to rotate. And I wonder-
Yep. So we've actually performed a wind speed maximum calculation that the motor shaft could sustain in this direction. If you go to the slide down lower there.
I think this goes along, your question goes along with
yeah,
I
yes.
think it's Mr. Singer's
Okay.
question about the two wheels, because we have the wheels side to side instead of front to front, and that would mitigate the force on those mirrors. But we did a calculation. This is the calculation on this central motor shaft. So the wind is hitting the mirrors, and we have this bending moment on this shaft. And this was a product of a lot of deliberation. We weren't really sure. This is a kind of a complex system here, because we have a press fit bearing on this motor shaft along with a coupler, and we weren't really sure how the force would act on this motor. Would it be directly on the motor shaft and start to break things inside the motor? Would this thrust bearing hold the load, which is what we opted to do the calculation for? Or would this thing just pull off?
Anything you can do to react that in a better way than a single moment on that one line is going to be enormously beneficial to the lifetime of your structure.
I would fully expect that that's where this thing is going to break. Frankly.
I have one
I
other.
like the calculations here, so you consider it.
Yeah, I have one really quick kind of question or point regarding kind of tangentially related to this, which is for assembly or manufacturing, are there any locating features or anything on the mirror to ensure that you install them like perfectly symmetrical about all these axes?
What was the end of the, were you talking about the reflection surface in the mirror?
I'm just talking about actually, using JB Weld to get these mirrors onto the axes. Is there anything that to kind of ensure that the assembler does that properly, seeing that it seems pretty important that all these mirrors are exactly symmetrical about both axes?
Yeah, I mean, this is something I was thinking about when I was doing the assembly time. And one of the things that I thought about would be if you had, something, you're pushing the mirror against, like, say, a wall or something, and you had a block or something to kind of set the distance of where the back of the reflection platform would be. That was one of the things I thought about that could make it faster in terms of assembly time and more precise, so that you're not trying to line it up by eyeball or something like that. But yeah, that's where we're at with that.
And also, I did want to add, this part of the mirror, the I-beam attached to the reflection platform, will be performed in one of the assembly plants that we will be using to assemble the module. So that would be more like an industrial procedure to get this together. And for the field, the person that will be doing the actual installation needs to attach this part to the shaft of the motor. So the addition of this I-beam to the reflection platform would actually be made in the plant instead of the installation site. So we expect to have people that are capable of achieving our tolerances.
All right, so sadly, we got to wrap it up there because we're at the end of our 45 minutes. But want to thank you guys for sharing your design with us. Job well done. I think I dropped it in chat. I love that you guys went to Home Depot and actually bought a mirror and tried to break it to see kind of, where its actual experimental failure points were. So I really appreciate that you guys were able to do that, even though we were remote this semester. So very good job. I have dropped in let me stop recording.